Assalamu alaikum. Welcome to the control system course. Okay. In this lecture we will be discussing continuing our discussion about the control system design in the frequency domain. Okay, in the previous lectures we already discussed some of the important aspects of the control system design in the frequency domain. Okay, so for example, we talked about concepts like the sensitivity, okay, which was defined by something like this. We already derived this in previous lectures. Okay, so the sensitivity, which is by definition how the variation in the open loop system will affect the closed loop system characteristics. It's one of the important characteristics of the systems, and we discussed shortly how we can observe controller design from a frequency domain point of view, such that the multiplication of the controller transfer function and the actual system open loop system transfer function in the frequency domain is high enough across the operating range of frequencies. And this is a condition in order to achieve a lower sensitivity across those frequencies. We also discussed about the error signal analysis. So we analyzed the error signal in the frequency domain as a function of R, for example, the reference input. And we also did our analysis including disturbance. Okay, so we include disturbance, we included noise in the feedback, and we did the analysis considering all those aspects, and we obtained the expression of the error as a function of frequency, as a function of all of those three inputs, and how the tracking error changes as a function of the reference, disturbance, and noise. And they require different requirements from the controller from a frequency domain point of view, and we already discussed all these aspects in our previous lectures. Okay, one more thing that we talked about was also the closed loop system characteristics. So, or in general, if we talk about the transfer function, which is the output divided by the reference input, okay, and if, let's say, this was a second order system, and if we were able to write it with the general second order system formula like this, 2 times zeta omega n s plus omega n squared. So if we were to write the transfer function in this formula, so we have two very important characteristics, which is the natural frequency of the system and the damping ratio, and we already discussed how this is related to the location of the poles and zeros in the S-plane, and how that actually is related to both the zeta and the omega n. But also one other thing is that we discussed how the shape of the frequency response of the system can also give us an indication about these parameters, and this was one of the important things. So for example, if we increase the damping ratio, okay, this peak will be reduced, and this peak is essentially at the damping natural frequency, which is omega n, like this. And also we talked about other characteristics like the bandwidth of the system. So this is actually omega, and this is T of omega, for example, if we are talking about the overall transfer function. So we talked about the bandwidth of the system and how this bandwidth is essentially related to the speed of the system, or the settling time of our system. So this was also one of the things that we discussed. So the idea here is that we want to be able to extract the transient characteristics of the system from the frequency response. So this was also one of the other important aspects that we discussed in our previous lectures. Okay, then we actually moved towards a pretty important topic also, which is the Bode plots. And the Bode plots are essentially just the frequency response, which is represented by gain and phase, but the gain and phase are just represented in the log domain. So the gain is basically 20 log to the base 10, the magnitude of g of omega, and the phase is just a phase. Okay, so plotting the gain and phase plots on a dB scale, and the gain particularly on the dB scale, and also the frequency axis is also in decibels. This is what you call the Bode plot. So it's just a frequency response basically. So it's there's nothing new here. But in this lecture we will also know why representing it in the log domain is pretty useful actually. Okay, and one more thing that we discussed was what we call the stability margins. This is one of the very important concepts in control, stability margins, and we talked in particularly about the gain margin and the phase margin. I'm not going to talk about them again here, but we will consider them in this lecture from the control design point of view. But the important thing here is to understand how we can extract the gain margin and the phase margin from the open loop frequency response of our system. And I'm stressing here is that the gain margin and phase margin extracted from the open loop frequency response of the system. So when we plot the Bode plot of the open loop response, we can extract both the gain margin and the phase margin. And the gain margin indicates how much gain the system can tolerate before it becomes unstable, and the phase margin indicates how much delay the system can tolerate before it becomes unstable. And these are two very important characteristics of systems when we talk about control systems and feedback control systems. Okay, so this more or less summarizes what we were talking about